there are types of discontinuities, and they are please contribute to the discussion even if you don't know. It's okay. So there are how many types of discontinuities? Yes?
3.
Yes, of course. 3. Good. And what are they? Yes. Infinite.
Infinite, yeah.
And the one with the hole. Removable. Jump, infinite, removable. Definition of continuity at the point. What should I write? What is the definition of continuity at the point, please? Anyone else? Please try. Michaela, would you like to try, please?
What was the question again?
Yes, definition of continuity at the point.
I'm unsure about that.
Okay, the limit from the left equals the limit from the right equals the function value at that point. This is exactly what I just said here. The limit from the left equals the limit from the right equals the function value at that point. So I'm begging you to redo the notes first and watch the videos. I'm begging you, please. The average rate of change of a function, of course, between 2 points is, can anyone dictate the average rate? Anyone?
Is it x2 minus x1 over y2 minus y1?
Careful, it has to be rise over run, not the other way around.
It's f of x2 minus f of x1 over x2.
Exactly.
Minus x1.
Thank you. Very good. Thank you so much. Okay, perfect. Now, the floor is open for any questions you may have. Let's start.
Can we go over problem number 36 from the homework, section 1.2?
Okay. Can you let me know what it is, or can you share, or you want me to find it?
Can you find it?
Yes, I can find it.
I can tell it to you.
Yes.
It's lim x infinity.
The limit as x approaches infinity.
Yep. And then it's 5x squared plus 5x plus 2 over, 10x squared plus x plus 1.
Perfect. So remember what we said. First, we have to plug it in. There are exceptions. There are exceptions to this rule, but 90% of the cases, 95% of the cases, we have to plug it in. So when I plug in infinity in these 3 terms at the top, which term is the most powerful?
X squared.
Yes, which means that these are completely useless. Not if I plug in 5 or 10 or 15, but if I plug in infinity, these are useless. They are too small. Much too small. Okay. So then, next, where does it go then?
You factor it out. Well, you force factor it out.
Yes. So in other words, when we plug it in, the numerator goes to infinity. Before we do that, you're perfectly correct, but we have one more step. The same thing here. So when I plug in infinity, I get infinity. We know that infinity over infinity, like 0 over 0, both have hope. It doesn't mean that the limit exists. We are only saying There is potential here for the limit to exist. Perfect. After we establish that, our next step is indeed factoring out the degree. It happens again that both numerator and the denominator have the same degree. So we had a similar situation in the notes last time. Everything was the same, just some numbers were different, but this is exactly the same. Each and every step is the same. That's why I'm begging my students always to redo the notes first. So the degree is 2 in both cases. You do not look at them as being connected. It just happens. It will not always be the same. But it happens that in this case, they're both the same. So let's see what we will have left. Because if there are 3 terms, I have to have 3 terms. 3 terms, I have to have 3 terms left in parentheses. So then, what do we write? Can anyone give us an idea?
5 plus 5 over x.
Yes, indeed. 5 plus 5 over x plus
2 over x squared.
Indeed. Take a moment and say, is this true? It's okay to take a moment and say, this times this, yes. This times this, yes. This times this, yes. Awesome. In the same way, you will have a 10. You will have 1 over x plus 1 over x squared. At this point, we simplify the x squared with the x squared. And now we have to remember something very important. And what is that? When x approaches infinity, a number over x, or a number over x squared, or a number over x cubed, or a number over x to the 4th, all these will go where?
0.
Yes. So since this is 0, and this is 0, and this is gone, what is the limit?
5 over 10.
5 over 10, or 1 over 2. And then we can say one important, these are my props, you can see. So you can say that when the limit of a function is a number, when x approaches infinity, this is guaranteed that y equals 1/2 is a horizontal asymptote. What am I saying here? Here's what I'm saying, and we're going to discuss this later in the next chapter. So 1/2 is here. This is y equals 1/2. It means that the function approaches 1/2 when x approaches infinity. So when x approaches infinity, the function will, I don't know that, I haven't checked, the function will come either from above, getting closer and closer to 1/2, or it will come from below, getting closer and closer to 1/2. That's why this becomes a horizontal asymptote. The function will approach either, not from both, because it's not going to be a function, right? It either approaches from below or from above. But it will definitely get closer and closer to 1/2. Good. Is this clear now?
Yeah, I just wanted to make sure I did it right.
Sure. Sure.
I did follow the notes and reviewed the video.
That's awesome.
And
That's awesome.
I got kind of confused still a little, so I just wanted clarity on it.
Absolutely. Any question, anytime, even if we have to repeat it, that's how we learn, by repetition. Thank you for the question. Next question, is there anything else? Anyone else, please? Anyone else? Okay, in that case, we're going back. I'm going to share my screen. I was doing something here. I'm not sure what I was doing. Where's my book? I had the book open. Yeah, it went away. Never mind. Okay, so we are moving on to 1.4. 1.4, starting from now, I would like you to understand that the material is starting to get more and more complicated. Different topics, different situations, a lot of work moving forward. Okay, So 1.4, we're going to talk about something called differentiation. We don't know what that means yet. But first, I want to talk about when a function is differentiable. We don't know what that means. Okay, so 1.4. Differentiation. These are major concepts. So remember, we looked at graphs. So here's an example of a function f of x. And we looked at many points on the graph, and we said here, the slope of the tangent line is positive. Here, the slope of the tangent is still positive, but this is much higher. The slope is higher here, more difficult to walk on it than this one. This one is less. So it's still positive. So positive. Okay, at this point, the slope is 0. Because at that point, the function appears to have a maximum. The slope is 0 of the tangent there. Then here, as you see, the slope is negative. Here again, the slope is 0. It has a minimum. When it has a minimum or a maximum, the slope of the tangent is 0. And then it goes back positive. So what I'm saying with this graph is that if you want to determine the rate of change of this function at this point, you will find it. It's positive. Here, you will find it, also positive, but a little bit smaller, not as acute. So this may be 2, and this may be 1, and this may be 0. I mean, not maybe, it is 0. But if we have a function like this, let me ask you the first question. Is this function continuous? Is this, I'm trying to readjust the other camera. Okay, is this function continuous?
Yes.
Absolutely, it's continuous, yes. But look what happens at this point. So remember, the tangent has to follow the function. So following the function, I have a tangent here. Following the function, I have a tangent here. So this one has a slope that is negative, and here is a slope that is positive. Although the function is continuous, at this particular point, we cannot determine the rate of change like we determine it here. This is called a cusp. I'm sorry, a corner. The cusp is like this, and I'll talk about it next. This is a cusp, like between two teeth, a cusp. So at this point, although the function is continuous, it has a corner. Because it has a corner, it has two tangents, not a unique tangent. So at this point, we say there is no rate of change. If there is no rate of change, we will say that f of x is not differentiable. It doesn't have a rate of change. It has 2, and that's not good. We need 1 rate of change. So the function is not differentiable. Okay. The same situation here. With the cusp, however, the tangent is vertical. Vertical tangent has exactly the same result. There is no rate of change, because the slope of a vertical line is undefined. There is no change here, no rate of change here. It's a vertical tangent, and the function is not differentiable. Again, one more example, and then I'll explain what this means. So here's another example. When the function has, it's of course not continuous. If it's not continuous, it has the same result, not differentiable, no discussion at this point. It's differentiable at every other point, but not where it's not where there is a jump, where it's not continuous. And here's the last situation, which is similar to this one, something like this. What does this mean? Exactly the same. At this point, there is a vertical tangent. So, a corner, a cusp, not continuous, and vertical tangent, the function is not differentiable. And again, in short, what does it mean it's not differentiable? Again, it does not have a rate of change. So if you ask me, let's suppose this is my distance function, and you ask me what was your speed, your instantaneous speed, when x equals 10, I'll say, I'm sorry, I don't have any. I cannot give you an instantaneous rate of change at this point, because the distance function that we used has a vertical tangent. Vertical tangent has a slope that is undefined. So not differentiable means there is no rate of change. So that's my page 3. Not differentiable. There is no instantaneous rate of change. Now, something extremely important is our next step, derivative. So we used 3 fancy words. Differentiation, it's the process of finding the derivative. I'll explain what that means. Differentiable means where a function has a derivative. Not differentiable is when a function does not have an instantaneous rate of change or a derivative. So now the derivative function equals the function that gives the rate of change instantaneous. The rate of change at any point where the function is differentiable. Where the function, is differentiable, which means continuous, no cusp, no corner, no vertical tangent. Okay, so when does this happen? Continuous and no corner, cusp, vertical tangent. So I want to look at a few examples, and this is on page, I have the page numbers 145, and enter. I would like us to, there is a lot of terminology, a lot of vocabulary, and we have to get used to it. So before we find anything, I just would like us to look at some graphs. So let's look at 27. The question here is, list all x values for which the function is not differentiable. Remember, not continuous, continuous and corner, continuous and vertical tangent, or continuous and cusp. Okay, so let's look at 27. What about this point, x0? Is the function differentiable at x0? Please try.